Okay, guys, in this portion of the video, I'm going to be explaining this ratio detector. And I got this, this is my own little tweak to the design, but I got the original design on a guy on eBay who's sort of modified, did some improvements on the ratio detector. And, sorry, not on eBay, online, yeah. And this is the fellow's original schematic. Now, the one I've done is a little different on the input. I've changed some values, and there's reasons for that, because I actually built this thing, tested it, and like a lot of stuff, you get information, and there's missing pieces of the information, so you're a little scratching your head, and I have to build it and test it and tweak it, and it looks like I've got something that works pretty good, so that's good. This looked pretty good, but he missed some things in the explanation, and then it left you really guessing. In the original article, I guess it was a Japanese guy. So this is the URL at the top here. You can see it. If you want to check it out, the original article, you can type that in. Hopefully it'll still be up when you come. But I'm going to scan through a little bit of it, and just in case it's missing when you get there. So you can read this, and it goes into the theory. This is the circuit that we just looked at. If we go down, there's a graph. I tried to zoom in on this graph by clicking and opening a new tab, but it's just as fuzzy. So it's basically the response curve of the output audio on the ratio detector. Okay, and I guess he claims that his little improvements have made it more linear and stuff. He goes into theory of operation of a basic ratio detector here, and so you can read that if you want. He goes into these vector diagrams. I'm going to show you a zoom in on that, because that did zoom in. Well, that's the zoom in of the actual, not the one we're building, but the conventional ratio detector. And these are the zoom in of the vector diagrams, how the voltage is decoded out of this detector. I've got another zoom in here of, again, it's more plots there, if you want to look at that. And this is, I'm just doing this in case you can't open that website up for some reason. This is a zoom up of an explanation he has for how he kind of came up with his design here. Okay, so again, I zoomed it. This is the zoom up. Hopefully you can read it. And so I'm going back to the article. So basically, he gets into the theory of how he made all that, how he came up with his design, and that's we're just showing that, and so you can read it. It's not very much to read, and hopefully that helps you understand it. Now, why did where I had the problem with his original design was I couldn't figure out, okay, he's got a coil there on the toroid. I built the coil. I tried to get that. I didn't have the exact Amidon coil that he recommends, the FT2361 12T. You can see it right there. Actually, I'll zoom in on this with this. There's a bit better. Yeah. Okay, so I didn't have that exact core. I had different cores that are probably pretty close, but the problem is you can see on the okay, right over here. I'll point it over here. You can see this part. I wasn't sure the 3.6 microhenry is this section or the entire core. So I didn't. This is where some of the questions come in. So what I did, because I have a good radio background, I know we really want to resonate this area here, the bulk of this core, the coil from end to end, and we want to resonate it here. So I have some cores that I'm going to show you in a bit what I did. So I made my own. I didn't use a toroid. I used a toroid at first, and it worked, but I found something else worked better with these form cores you can get on eBay, and you can wind your own. So that worked out pretty easy, and I got good results at the end. I also ended up changing, because I assumed this was 3.6 for this part. I changed this here. I started with something close to that, and then I resonated with this, but I found what happened. I found using 1 microhenry here and resonating it with 50 picofarad, which I think resonates higher, but the resonate of this coil goes through these two loops of coil, which is a core, so that'll add to this. And when I did my calculation, it looked like it was, if I just resonate this with this, I'm around the 20 meg, roughly double the frequency, but I didn't measure what happens here. I didn't get too far into it because it worked. You're going to see how I did my measurements later, and you'll see what this actually does, because there's a little tuning it this. Actually, I didn't use a variable cap. I used a 50 picofarad cap and a tunable coil here. Again, I got that off eBay. I used the same coil form for this one as I did for this part here, and it was very easy to do, and it worked. It seems to work good. Okay, so this is what I've done so far, and I'm going to show you now my the coil that I made here and how I did it. Now I have part of the breadboard used for this detector. It's kind of in the left side. Doesn't include these crystals. Just this, you know, this guy, some of those guys back there. Not the chip. The chip's not needed. That's something else. So that's my inductor there. Let me see if I can zoom. I don't know if I can zoom in on that. Oh yeah, yes you can. So that's the inductor I hand wound. So there's, you know, there's 5 total connections on that inductor. So I can swing around a little bit and see. You can see there's 2 in the front, the brown and the white wire in the front, and the blue, the white, blue, and the orange are the other 3 taps on the other side. I'm going to show you the schematic, okay, and then I'm going to tell you how I wound that coil and where you can get them, okay. So here's my schematic. It's spin off from the original, and you can see what I did with the. Let me grab one of those cores. Okay. Yeah, I bought a pack of these forms. Okay, on eBay. They're blank forms. They got the ferrite, tunable ferrite in the center, and so there's 5 connections on these, as you can see. And so what I did is starting from, you know, bottom, I guess, of the coil, I wound 10 turns, and then I took a tap off here at this point where the cap goes. Okay, the 50 picofarad cap. I made a tap there, and then I did another turn, and then another tap, another turn. Okay, another tap. So the tap connects to this 1 microhenry coil, and that tap connected to this cap. And after that, I did 10 more turns. Those go this to this side. So it's very simple. I use number 26 gauge wire, and so that was the coil. You know, I use these forms. You can get these off of AliExpress or eBay. This guy's selling them. I guess you could just type in tunable coils, and you'll probably find them. I think the one, there's another guy sells a pack that are kind of pre-wound. These are good for like FM at the IF frequency of 10.7. They'll tune nicely with maybe a 20 picofarad cap in parallel. It's 2.6 to 6.8 microhenry. Again, you can search for them. They're the same thing, except these are got wound with the, you know, they're already pre-wound. But this is not the value that we're looking for exactly. The one that I have is, you know, I kind of customized it so I have all those taps. So I used all 5 terminals on that coil form. So once you wind that coil, you know, what I found, because the original diagram was, I think it was saying 3.6. I tried something like that. I think I got some results, but I found this and this combination, as you're going to see me how I tune it, this does a little bit better job for tuning. At least these are my experiments and my tests. And everything else is pretty simple. This 160, I think I changed that. Let me just check what's on my real board here. Yeah, that I changed to, let me give you the right value. I've got a 56 cap in parallel with a 10, so I've got about 66 picofarads here. Okay, so change that. You don't need a variable because you're just this core is actually variable. I should have drawn it a bit different, but I have a variable tuning on here, so we just need two fixed value caps, 66 in total there. Okay, and then these diodes I used 1N60P. They're very similar to the original ones. 1N60, it doesn't really matter, but I'm going to tell you a little bit about the diodes, and I found this by accident on an eBay site, not an eBay site, a website. Some guy talking about these diodes, he was saying that there is 2 versions of 1N60P. One is, I think, a Schottky, and one of them is germanium or something like that. And he said he's done a lot of tests on this with crystal radios and detectors, and he said The larger ones, the 8mm long glass body diodes, are the better ones. These shorter ones, he's found they're not as sensitive, and sometimes they won't pick up for decode. Now, I don't think I have the best ones here, but it still works. I wouldn't mind upgrading these to get the real ones. Another part number is the 1N34. Again, get the big ones, like the 8mm. And I think 1N270 is also a detector diode. You want the germanium larger glass body diodes if you can find them. Some of the smaller ones might work too, but this is what I found in his article. He was saying all the tests he done, he said the larger glass body diodes are the better ones. They're more sensitive. So the rest of the circuit you can build. It's you get the 300 picofarad caps, you get the 3.3 microfarad cap that does sort of like amplitude modulation limiting, and then if you're going to run it to an ALC, you're just getting a positive voltage on that tap point, where it caused the ALC is the automatic level control feedback that controls the gain of your IF stages for the 10.7 megahertz IF amplifiers that you're going to be driving this with. And that's optional, I guess, but that'll help control your audio level. If there's any up and down in your RF level coming into this thing. And then I've got the audio output there. So I'm going to show you what kind of results I've got so far with what I've built on the breadboard. I have it on a breadboard right now. I'm going to put it on a PC board soon, and then do some final testing on it. So what I'm going to do is turn on my scope. These, let me just see if I can zoom out now. It'll probably be a little steadier. And let's put that on scope. There we go. Okay, so what we are on is we're using the time 1 probe on the audio output. So audio is not going to load it down. This isn't going to load the audio section or anything, because but when you're doing RF measurements and stuff, sometimes the time 1 will load stuff down, and so you got to be careful with stuff like that too when you're doing measurements. And I think the so the also the bandwidth of most 1x1 probes, it's only around the 5 megahertz range, so keep that in mind. So we're on the 10 millivolt scale, okay, and we are on DC. Let me just make sure that's true. Yeah, DC coupling. Okay, now, so this is connected to the it's on my circuit. It's the audio output right at the in between those 5.6K resistors. So that's where we are. We get the two 5.6K resistors, as you can see, and it's coming to my probe there. Okay, so we are looking at that signal, and what we're putting in is to the input side. It goes to, let's see if I've done that on my schematic. Okay, one thing I missed on my schematic, you see where that center tap is? I have a capacitor. I have a 0.068 microfarad. You can go with a 0.1 microfarad. I forgot to draw that in right at the center tap to ground, just to, because it's yeah, that's what I've got there. So just to block any DC components. Okay, so I'll change that on my updated schematic later, but I've got it on the breadboard. You can see that. If I can zoom in on that cap, you'll see what I'm talking about. This is the cap I'm using. Can't really see it very good. It's this cap right here, this guy here I'm wiggling. Yeah, this guy here. Okay, so that's where I'm feeding in. It goes to the center tap. Okay, and then we're sending our signal in right. Where's my probe? Right here. That's the input to this thing. Okay, and that's coming from, where's that coming from? Let me zoom out, and let's see. I'm connected over to here. That scope probe is the output of this signal generator. I think you can get these for about $60, $70 US or something on eBay. And I've just got it set to 10.7 megahertz. The amplitude is 0.1 volts, as you can see, and the it's a sine wave I'm pumping in. Okay, and now what I'm going to do with this, I'm going to up to 10.8. And I'm going to go down to 10.6, and we're going to look at the output on my scope. So let's see if I can go up. You see if I can go, yeah, see, I can vary the number there. Okay, so we're at 10.7 right now. You see what's happening? We're at 10 millivolts. Okay, I'm going to go down now. You see, our signal's gone down a little bit. It's a little bit bouncy. We've gone down to just almost minus 10 millivolts. That's 0 DC, and we got a plus 10 millivolts. Okay, you see that? Now, how does this thing tune up? Okay, so you can see how it's working. Now I can put higher levels, but I think I can see changes even when I'm running as low as 50 millivolts input. Right now I'm running 100 millivolts input to this ratio detector. Okay, so this is the nice thing about using the coil that I made. I've got a little tuner here. Okay, I'm going to start messing with this. Okay, I'm going to tune that just a little bit. I want you to watch this output as I tune that. Okay, you see it's going up, and I can go down. So I set that to there. Now, okay, so that's how that works. Now this coil here, and you could make that tunable too. This cap with this 50 picofarad cap and this 1 microhenry coil. The way I selected these is so when you go up in frequency and down in frequency, you want that to be kind of proportional. See, it's maybe it's 8 millivolts down or something, and it's 8 millivolts up. By selecting those correctly, it'll be sort of symmetrical. That's what I found. Okay, there's no really explanation how to tune this thing. It's just me messing around with it, and you know, I have a fair bit of RF background, so I was lucky to get it working fairly quickly, and I think it's working correctly. It looks like it's pretty sensitive. I don't know how sensitive these things actually are. I've heard some, you know, seems like there's a little bit of discrepancy, or it's hard to find good information on this. And a lot of theory behind it doesn't tell you that. Like if you'll see hundreds of videos on this ratio detector telling you, oh, they'll load you up with math, but they don't tell you, okay, here's your minimum, maximum, or you know, the minimum inputs you got for this thing that will work. And I bet you most of those people pumping up the theory on this, they couldn't build one that works. It's just that way. It's just like there's tons of guys writing theory and teaching, and yet they don't have a working circuit or something they can show you that'll work, and you know, and give you more details on it. So that's where sometimes the disconnect is, and that's why it's hard to sometimes build stuff, because you don't have a working circuit. So anyway, here we go. We got a working circuit. I'm going to go to the next phase in this, and I'm going to put it on that little board I got. I'll show you. I started working on it. Here's the board. I'm going to solder it all on. Okay, that's the little board. Okay, I've started it on the coil and one of that 50 picofarad cap. I think it is. Yeah, I don't know if you can see it. Yeah, you can see the cap 50. So I'm going to finish this off. It won't take too long. And then I'm going to carry on, and we're going to measure it on the board, because there might be interaction. I hate working on these breadboards, because I find they're so intermittent, and I'm finding also a lot of these probes from China are very intermittent. It seems like the connection between this little you know, spring-loaded thing with the clip doesn't always mate with that center thing very good. It seems like it's highly intermittent. I'm just always fighting with them. So just another word of caution there is sometimes you buy cheap stuff, you have a lot of headache. And even these breadboards, most of them are crappy actually, and there's a few good brands. I think it was EIA, I think, on eBay. Some guy had a whole article on breadboards and quality of breadboards and everything. So I'll try to get something better. This is probably one of the crappiest ones you can get, I think. When I got, oh, maybe there's more crappy ones, but it's not that good, and you get a lot of headache with them. Okay, so oh, speaking of breadboards and wire, I use what I'm using is category 5 in Ethernet cable wire. It's a solid copper wire. You can get, I think there's 4 pairs of 2 like that in a bundle, and it comes in a. Let me show you the wire. Yeah, here it is. Let me grab the wire. It's a. So I think you can get a roll of. I think this is a roll of 50 feet or 100 feet. It was $40 at Home Depot. So this is what, you know, what comes off it. Okay, it's category 5 solid copper. Yeah, there's 4 pairs. You can get category 6, which is a little thicker. This is 24 gauge copper. The category 6 is 23 gauge, it's slightly thicker. I don't really know if you need thicker, but if you want it, yeah, and it was $60 instead of 40. These are Canadian prices, so. But so this is just a tip for you where I got my wire, because I was having a hard time finding some wire locally here. Okay, so that's now I'm going to carry on build the rest of this thing, and then we're going to show you what's going on. Okay, thanks. Okay, here's our finished ratio detector. All I need to do is connect the input and output leads to it to test it. So the output is on the right hand side there. You can see those two 5.6K resistors that go into that common pad. That's your output. You can see that electrolytic cap, that's a 3.3 microfarad cap. It's on the drawing. And if I, right beside it, to the left of that 3 microfarad cap is one of the 300 picofarad caps, ceramic cap. It's marked as 301. You can barely see it. Of course, to the left of that electrolytic, here's your two detector diodes, the 1 and 6OP. And to the left of those is the two 150 ohm resistors. And you can see, instead of using the 10 picofarad in parallel with 56 picofarad, which gives you 66, I used the 68 picofarad cap. That should be close enough. And way in the back there, in the corner, you can see a 50 picofarad cap right beside the green coil. And you'll see that in the schematic. And my transformer, I've got it wired up here. Okay, it's more like an auto transformer because it's not like a secondary and primary. Everything's kind of tapped on the same coil. So you can get a close-up there of how I did it there. But you can hand wind these. You can get the forms off of AliExpress or eBay. And I rather like these forms because they got a little, you can see that little elastic band in there. Makes it easy to turn, and of course if you ever lose that elastic band, you can just cut a piece of a regular band and just make it really thin like that and then jam it in there. But these don't break too easy, these cores, because of, you know, that's why I like these ones. Some of the other ones are, you know, they break easy and stuff as you're turning them. So anyway, that green inductor is 1 microhenry. That's the value I settled on. So I'm going to test it like this with the leads on this coil, and the reason is those leads may make a difference. So I'm going to first do the initial test like it was on the breadboard, and then I'm going to come back in, take those off, and put that right down and see if there's any difference, because I know with RF, you know, it's only 10 megahertz, 10.7 megahertz, but might make a difference. Okay, so I'll test, I'll show you what I come up with after I connect the leads on here. Okay, now you can see I've taken the wires off that coil and soldered it right onto the board. When I did that, yes, I did have to adjust the core a little bit, maybe a quarter of a turn or something, just to get my baseline down to close to 0. Let me see, it's a little off. Okay, oh, there, it's pretty close to 0. Okay, now what's happened? Okay, I'm at 10.7 now on my generator. I'm going to go to 10.6. Okay, that's 10.6. You see how much it went up? About 10 millivolts. And I'm going to go up to 10.8. See, it's only going down maybe 5 millivolts. It was more proportional before when I had it on the breadboard. So I'm going to try to adjust. Again, I'm going to go back here. See that green coil? I'm going to try to adjust that. I'm probably going to leave the coil the same. I'm going to try to adjust that cap. Put add series or like parallel cap, or take some off. I'm going to see what happens, okay? So let's see what happens when I do that. Here we are again. And I had some mistakes. You see this, I'm going to use my little pointer because it's a little easier. You see that yellow cap? Well, I had a solid line underneath there. I forgot the cap. There's a coupling cap to the center of the coil. So I added that in. But that wasn't the only mistake we made. The other one was more subtle. This coil was on, I had it going, let's see if I can get this a little bit closer because it's really hard to see it. Yeah, right here. Okay, so I had the coil going on this pad to ground, but so really what I wanted to have is the cap on this side to ground, and I used to have that cap. This cap used to be on this side to ground. So I just flipped them around because that's how I had it on my breadboard layout. So I'm going to show you on the schematic in a second here. Okay, so we're on the schematic now. Okay, so let me get my little pointer. So the coil's on the top, okay? That's how it should be. But when I wired it, I had it flipped. I had these two flipped around, this cap and the coil flipped around. I guess there's a slight impedance change. I probably could have tuned it by messing around with the coil and the cap and got it to do the same thing. But just by flipping it around, my original value was still valid, 50 picofarad and 1 microhenry. Those two values work in here if you do it this way. So make sure the coil's on the top, don't get them flipped around. It's an easy mistake to make. Everything else is self-explanatory, except for this part here. Let me just change this. Okay, this cap was, I changed that to, so we're just getting 68. Okay, 68 picofarad fixed value. You don't need a trimmer here. Let's change that too, just so we've got it updated. Okay, so that's it. You don't need a trimmer there. As a matter of fact, there's only this one trimming coil to adjust, so that's nice. And everything works okay. Same results. Now, if I go back to the finished circuit here, okay, I'm gonna go back, power the thing up here, scope. So this thing shuts off automatically, doesn't give any warning. Okay, so we got our base 0 line, 10 millivolts. Both scopes or probes are set to ×1. From the generator, I'm generating 0.1 volts. I'm going to go up to 10.8. And you see, my scope's a bit slow to react, but that's just the scope. Okay, then I go back to 10.7. I'm going down to 10.6. Pretty close. I'm pretty happy with these results. Probably could you could probably trim that 50 picofarad cap a tiny bit if you wanted to. If you really wanted to get the balance just perfect, but it's good enough for what I'm trying to achieve anyway here. And yeah, so yeah, you can go lower. And so I've got the generator set to 0.1. Okay, 0.1. Let's go back to the generator. 0.1 volts. See if I can get that to focus. Yeah, there, 0.1 volts. Let's take it down. Let's take it down a bit. Okay, amplitude. I can get it. I can kind of see the change in the scope at 50. So back to frequency here. Okay, now let's take a look what we got. Okay, pretty close. Maybe the baseline's changed slightly because of it's picking up the signal from that. But let's go up to 108. Yeah, you can see a change. See, you can see a bit of a change. It's probably about maybe 3 or 4 millivolts or something. 3 millivolts. Go down. Yeah, you can definitely see change. So we are getting, with as low of a drive as, and maybe it's even lower because my scope is at the maximum sensitivity, and it's not the the best scope in the world. It's okay, but we are getting a change even at these low levels, 50 millivolts injection. And one would think, well, doesn't the diode need regular diode 0.7, and maybe the germanium is 0.3 or something. These are, I think, the ones I got in here, I think, are Schottky. I think they're 0.3 volts or something in that range. So it's working okay. It's gonna decode it for sure. It's gonna decode FM. But again, if your RF level's changing on here, from really low RF injection of 10.7 to high injection, you're gonna get different levels. So you're gonna get different audio levels, because you would still have to take the ALC line and feed it back to control the gain of your IF amplifier. Another thing you could do is just make sure your IF amplifier is limiting, so it's not changing in value. Then you're okay too. So you wouldn't need the ALC line then. Okay, now what we can do, that ALC line, I can sort of demonstrate that to you. So what we are now is at 0.05 volts sine wave, peak to peak. We are gonna yes, if I can get that. I'm going to solder another wire on my board just so we can do this test properly. Okay, I'll be back in a second. We're back again on our circuit. I soldered, let's see, this wire here. Okay, this white wire. It's to this pad here. On the schematic, it's labeled ALC. So you can see it on the schematic that I have. We're going into our scope here. Same feed going into the input of this the ratio detector. And now what we're going to do, okay, we're going to look at what we got on the scope. We get, okay, basically 0 volts roughly. Now on my generator, so you focus that a bit, we're at 1 volt or 0.1 volt. Okay, so what I'm going to do is I'm going to go up 0.1 volt at a time, and we're going to see what happens to the ALC line in DC. Okay, so we're going to go to 0.2. So now we're at 10 millivolts. Okay, that noise that you see in the middle, it's not my circuit. It's something else with either the scope or the generator. It's something, I haven't figured out where that's coming from exactly, but it's not the circuit. It always seems to be there. Okay, so I'm going to go to 0.3. 0.3. See, it's jumped up to 30 millivolts now. Okay, All I'm changing is the amplitude of the 10.7. I'm not changing the frequency. It's at 10.7 megahertz right now. So I'm going to have to go to a higher range now here. And if I could go down to it. So now 50 millivolts per division. So let's go to 0.4. Yeah, you can see it jumped up there. 0.5 volts in, 0.6, 0.7, 0.8. Okay, let's see. Keep going down here. Now we're at 200 millivolts a division. Okay, that gone up a bit. Now we're 0.9 in, 1 volt in, 1 point. You can see it going up. 1.1. It's going up slightly. 1.2. Let's go up to 2 volts. So it happens. Okay, 2 volts. You can see it's up there. 2. It's up to 400 millivolts. Okay, let's go up to 3. 3. Okay, well, that's about 600 millivolts. Okay. So you can see. Let's see how high we can go. There's 5. Okay, so we're about 500. I'm just going to see if there's I'm going to go up by 1 volt at a time now. We're up to 4 volts. Okay, 5 volts. Oops, 5 volts. Let's skip 6 volts coming in. 7, 8, 9, 10. So you get the idea. You probably won't be ever needing that much, but that's over 1.5 volts. You know, it's probably about 1.7 volts coming out of there. So that's your ALC line. Okay, now let's go in the negative direction. See what happens here. Well, actually, you won't be able to. The lowest you can go is 0 volts, right? So if I've set it right, again, I'm not sure if you want to set it. I think I've calibrated. My scope doesn't stay on the 0 line perfectly on all the scales. It's just the calibration of this scope. Let's go down here, back to 10 millimeters. So it kind of goes back to the 0 line when I go down. So if I go down up at 0.1 volt right now from the generator, I'm going to go down to 0.9. Okay, 0.3. I'm at I'm at 0.03. 0.02. This is what happens at 0. So not much action happening in the really low levels, which you'd probably expect, right? But once you get start getting over, now we're moving up. Like this is 0.2. So it starts moving up kind of quickly there. So that's your ALC line. So I hope this video has been helpful. I'll probably make some other detectors. This one is my first one I've made. It's the ratio detector. And it's, I'm using a little bit of techniques from the website I found from Japan, and got my circuit working. I'll do a Fossley-Seeley detector. Ratio detector is supposed to be a bit better, but I'm going to try the other one just to see what kind of results we get, and then I'll maybe do phase lock loop, because phase lock loop is supposed to be maybe the best for linearity and stuff. So I hope this video has been helpful. So someone actually wanted to make a practical unit. I'll try to send links maybe where you can get these forms on eBay. But if you search for tunable forms, you'll probably see something that looks exactly like this. And the idea is you don't have to use exact values. I have on my schematic, for instance. Let's see here. If you find a form, and you just want to make sure that you get this resonating around 10.7 megahertz. So you don't want a coil that's too big, because it might self-resonate at a lower frequency than 10.7. That's your main thing. So if you get something that's a lot lower than mine, you'll have to increase this cap so it resonates. But that seems to be the most critical thing. But I would try to stay with the coil that you can get on eBay. And let me see something here. The measurement value of this coil that I had. Let me just check that for you. Like the measurement of inductance from end to end. Let me see what I measured. Okay, hold on for a second. Okay, so I measured about 3 microhenries on that coil from end to end. And what we got here is a toroid coil that I wound. This also measures 3 microhenry from the end to end, and of course you see this the center tap and one for the coupling cap in the input, and the coil, 1 microhenry coil in the input. You could use a coil like this, but this isn't tunable, and so you'd have to now make your capacitor, instead of use a fixed value of 68 picofarad caps on the output, you'd make a tunable cap to so you could tune this, and that should work well too. It may even work better, but I don't know. But I like the tunable thing because it just seems to make work well, and it was easy to wind that coil on there and everything. So, if any of you need maybe for me to make a video on how to wind the coil, let me know. Especially like this one here. This one is in that document that I showed you online, with the photograph from the Japanese fellow who made this. This is wound the same way, so there's no magic there. But this isn't hard either. It's really the same idea. It's just start with 10 turns from the bottom of the coil, and then you make a tap point, and then another turn, and then you make another tap point for the center, and then you make another turn, and another tap point for that. I guess it's for the coil, so on the higher point, and then 10 more turns. Okay, and that's it. So, but I have that sort of in the schematic. I think you'll be able to follow it. So basically, that's it. That's how you make a ratio detector. I hope you enjoyed this video. Take a look in the description below. I'll probably have a few more links to any other information for other videos I come up with this. I'll probably have some IF amplifier videos. I have an amplifier I made 60 dB gain at 10.7 megahertz, and I may use that to drive this, but I'll make a video on that as soon as I get time to do a video. And then I'll try to do a phase lock loop detector as well, for that'll be a natural progression for all this. Okay, stay tuned. Bye now.